Alan so that he can begin today's course lecture. So to begin with, I'd like to tell you a little bit more about IEEE Communication Society, also known as ComSoc. I know many of you are already ComSoc members, and we thank you for your membership. If you're not currently a member, now's a great time to give membership a try, as you will get the remaining part of the year membership for half price right now. So it's a great way to try out the many benefits of ComSoc, some of which I'll talk about right now. And ComSoc is comprised of over 27,000 global industry professionals. It promotes the advancement of science, technology, and applications in communications and related disciplines while maintaining the highest standard of professionalism and technical competency. IEEE ComSoc is paving the way in the development of strategic and technical conversations in the emerging areas of 5G and future networks, IoT, big data, green ICT, machine learning, and AI, and so much more. In addition to impactful one-day events and workshops, the Society holds numerous conferences, local chapter events, and tutorials throughout the year, many of which over the last year have been virtual, making it a little bit easier to participate in. IEEE ICC and IEEE GlobCom are our two flagship conferences offered each year. Up first of those is IEEE ICC 2021. That's actually going to be taking place completely online. That's a virtual conference this year. That's happening in June. Registration is now open for that conference. And then later this year in December, we have IEEE GlobCom, and that is planned to take place in Madrid, Spain. And as you can see on this slide, there are many other great benefits of ComSoc membership, such as digital subscriptions to superior publications like IEEE Communications Magazine, which is included with your ComSoc membership. There's also valuable members-only content that's available to you, including an excellent selection of video presentations on IEEE TV. And you can learn more about ComSoc, all these valuable programs, and full details on the benefits of membership on our website at comsoc.org. At this time, everyone should have received an email from me with a PDF attachment. That is your course handout for today. The course handout includes at the very front, you'll see Alan Benske's biography, followed by the PowerPoint slides that he will be presenting today. And then at the very back is a list of acronyms, commonly used acronyms for your reference. If you did not get that email, please let me know. It was also available for download on the WebEx session information page. I would be happy to resend this email to you and with the course handout should you need it, so just let me know. Everyone who is participating in today's course will receive a certificate of participation. You can generally expect to receive that within the next 1 to 2 business days. And in addition to that, you can qualify to earn 0.6 IEEE CEUs for your participation today. In order to qualify for those, you do need to complete all of the fields in the online course evaluation form that's provided after the live session today. And then you'll receive a separate certificate in your email in about 3 to 4 weeks indicating the CEUs that you earned for today's class. Even if you don't need the CEUs, we really do appreciate receiving your feedback on our courses as we're constantly looking to improve our offering. So if you could take a few minutes, it's mostly multiple choice, not too many questions. There are areas for you to provide written feedback if you'd like. Again, we'll provide a link to that after the live session today and in my follow-up email to you as well after the session. We are recording today's course. I try to get the access instructions out to you as quickly as possible, usually within a few hours of the close of the live session. You will have access to view that recording as many times as you'd like through April 18th. It is not downloadable. It's a streaming video. Please remember, it's for your personal use only. It's only to be used by those who have registered for today's course. And if you have any problems accessing that recording, just let me know. I'd be happy to assist you. In general, most people don't have any problems with the recording access. Now it's my pleasure to tell you a little bit more about the developer and instructor of today's course, Alan Benske. Alan has been an IEEE ComSoc training instructor for many years now, and he's been bringing his extensive industry experience working in analog and digital design, management, and marketing to our program. Alan has carried out projects for various military and consumer applications and led the development of 3 patents on wireless distance measurement. Alan has taught electrical engineering courses and lectures on radio engineering topics. He's the author of 2 books, Short Range Wireless Communications, which is in its 3rd edition, and that's published by Elsevier, and Wireless Positioning Technologies and Applications, published by Arctic House. In addition, Alan is a contributing author to 5 other books dealing with wireless communication. He's a senior member of IEEE and an IEEE certified wireless communications professional. Again, as I mentioned earlier, a more complete bio on Alan is available in your course handout. It's also available on the Comstock training website. Now, before Alan begins, I do want to talk about how to make the most of having access to Alan's over 40 years of expertise in this area, and that's by posting your course-related questions to him in the Q&A section. I've got a screenshot here of where you can find it. Look in the upper right-hand corner of your WebEx window for a drop-down menu to select Q&A. If you're on a Mac, it may appear a little differently. Check the lower right-hand corner of your screen for a box with a question mark in it. If you click on that, that'll open the WebEx panel for you. I recommend that you have that open during the session today so that as your questions come up during the session, you can easily type them in and submit them to the instructor. Now, we ask that when you do submit your questions that they please be brief, direct, and that it's relevant to the content being presented in today's course, and that it's a close-ended question. Also, it's really helpful if you can make note of the slide number to which your question is referring to, so that Alan can easily jump to that content and address your question. Now, he's going to try to address as many questions as he can during the live session today. Anything that is not addressed, however, will be collected, and I will share those with Alan, and then the entire class will receive a copy of those questions along with Alan's written responses in an email in the days following the course. Now, if you have more questions, perhaps outside of the scope of today's course, we have some other resources we recommend. There's the Communication Society on LinkedIn. There's also IEEE Collaboratech, which is a great platform in which you can search for groups or communities of related interests. You can also connect with fellow IEEE members through the membership directory, which resides within Collaboratech. And you can find Collaboratech by going to the address I've noted on the screen here, or you can simply search for Collaboratech on the IEEE.org website. As for the timing of today's course, the day's broken into 2 sessions. We're going to have a hard break around 12 p.m. Eastern. So I know we're all in different time zones. To give you a better idea of that, it's going to be in about 3 hours from now. You can in about 3 hours from now, you can expect an hour-long break, and then we'll have some shorter breaks in the first and second half of the course for about 10 to 15 minutes as timing permits. Some final reminders: please share your questions with Alan to Q&A. Anything not addressed will be addressed in email to the entire class in the days following the course. And then if you have any technical problems, need a copy of the course handout, questions about CEUs, please send me a chat message, or you can send me an email and I would be happy to assist you. That concludes everything that I needed to cover with you. So now it is my pleasure to hand things over to Alan so that he can begin today's course lecture. So Alan, just let me know when you're ready and I'll hand over the controls.
Okay, thank you very much, Tara, and I'd like to welcome all of you to the course. As I'm sure all of you know, this course is about estimating the position or location of a person or an object through reception of radio signals. The terms positioning and location are often used as synonyms. In other words, that people don't normally distinguish between them. However, they can have particular meanings, and I try to give them the following meanings, where positioning would be the more general term relating to object orientation or distance, whereas location gives specific local or global coordinates or an address to indicate what is in space. There are a number of physical characteristics and technologies involved in positioning and location, and we cover the most important ones in this course. We'll leave it up to the system designer or the user to decide which ones are the most applicable for his need. The course is arranged such that we start with the fundamentals, the basics, the very basics, and then we go on both to some ways of using these basics and also the various uses of positioning and location, where the knowledge of the basics is necessary in order to understand what comes after that, particularly for the cellular, short range, and indoor positioning. Near the end of the course, we'll talk about fusing different methods of location and positioning, and then we'll summarize the course at the very end. There are several features of a signal or a waveform which contribute to positioning and location, and we'll examine those first. We're talking about time resolution, bandwidth, and averaging. The distance and signal direction are used for target location, and this involves various geometric classifications. And finally, we'll discuss the basic measurement classes, which are propagation-derived methods, time of flight, time of arrival, time difference of arrival, and phase of arrival, received signal strength, and the wave front direction. So let's get started now with the time resolution. This is probably the most obvious to understand. Here we have a simple radar system. Perhaps the most familiar distance measurement application is radar. And a clock is needed. We have a digital clock here which has pulses, as you can see. This TC is the period of the clock, and its inverse is the frequency of the clock, and we assume that measurements can be made on the rise of a clock pulse. So here we see that the transmitter sends a very strong pulse in the general direction of a target, and a very weak pulse will be bounced off the target and return to the transmitter, to the radar station. The actual time that it takes, the round trip, is between the start of the rise of the transmitter pulse and the start of the rise of the receiving pulse, but this cannot be determined exactly, and the resolution that this can be determined depends on the clock rate. And here we see here the fact that the transmitting pulse is measured by the clock on the rise time of the pulse, and the return pulse can only be detected by a rise time of the clock, so there's a discrepancy between the actual time of flight of the pulse, the back and forth time of flight of the pulse, and the measured time of flight of the pulse, which gives the obvious conclusion that the higher the clock frequency, the higher the possible resolution of the time of propagation time, and from the propagation time to the distance by multiplying the time by the propagation speed, generally the speed of light. In this particular case of pulses, it's very easy to determine the actual point when a signal is going out. This is called an epoch. The time instant that is being measured is called the epoch. It's measured here on the rise of the timing pulse. The epoch may also be field boundaries in a protocol frame, or it can be found by correlation with matching a local generated pseudo-random waveform. But in any case, as we see here, in order to resolve time, there has to be a way of determining a particular point on a pulse or on a a signal in general. The second quality that we're going to take a look at, very important, is the bandwidth. And the bandwidth is associated with determining the time at a given instance. The bandwidth is another parameter which is important to determine how close the timing can be determined. Here we have on the two sides of this slide, we have two different bandwidths. We have multipath signals, pulse, which are sent out and reflected over several different paths, reflected by objects within the path. The first pulse, normally considered to be the line of sight pulse. Let me get down the pointer here. We can see here at the rise of this pulse, we see a relatively sharp rise, and this would determine the first returning pulse. And then there are other pulses even stronger than the actual line of sight, which may be blocked or partially blocked by objects in the path between the transmitter and the receiver. But in this particular case, with this particular pulse width that we have here, or sharpness of the rise of the pulse, we're able to determine fairly accurately the time of arrival of the pulse. Of course, there will be noise. Noise isn't shown here, and this will also make guidance as to the actual time of arrival. Here, all the pulses that have been reflected are discernible, and it's possible to determine which pulse was received first, and therefore determine the time of flight of the pulse between the transmitter and the receiver. On the right side of the slide, we have a bandwidth of only 20 megahertz, and here we see that the pulses are blurred together. The return pulses are blurred together because the bandwidth is relatively short, considering the times between the different pulses. The variance of the time of arrival that can be detected is a function both of the signal to noise ratio and of the square of the bandwidth, as we can see here, and also of a particular constant. So here we see the fact that the greater the bandwidth, the higher the accuracy with which a pulse can be determined. Therefore, signals, radio systems that have wide bandwidths can determine the timing of the transmitting and receiving, essentially the receiving pulses, to a much greater accuracy than those of having a low bandwidth. And of course, the signal strength related to noise is also an important factor. The rise time itself, within which a pulse can be determined, is also a function of a bandwidth approximately here. So this is the importance of bandwidth in the accuracy that a signal, I'm talking about pulses, but as I mentioned earlier, this could mean a measurement within a protocol between protocol fields, continuous signals. Okay, with all the importance that we talked about of bandwidth and the clocks, it's possible to increase the accuracy of signals by averaging the signals over a period of time. That is, trading time for bandwidth or for clock rate. Here is an example of averaging the noise out. Noise is the ultimate limitation of communication effectiveness, and it's a component of all wireless signals. So through averaging, time can be traded for bandwidth. The ordinate here could be any quantity. It could be the time of arrival, and here the abscissa, the x-axis, could be the number of samples. Okay, if we is here, we assume that we have a certain number of samples. We have here 10 different samples. Because of noise, each sample has a different, maybe a different time and not amplitude as shown here. It could be a function of time. So we may be measuring time of arrival a number of times over a particular time length, as we see here. And we note that the true value of the time of arrival, shown by this dotted line here, and the average value, these times of arrival can be averaged, and this average itself is also a random value. And the more samples that are taken, the longer period of time that these signals are repeated and measured, this will bring this average closer and closer to the true value. This is expressed by this expression here. The variance of the value that we want to measure, the variance of this average value is a function of the variance of the signal itself, which depends on the noise on the signal. If there were no noise, then all these x's here would all be at the same value, the true value, but because of the noise, they are different because of random noise. And we see here that the variance is of the average is the variance of each individual. Here we're talking about, say, time of arrival or amplitude divided by the number of samples. The standard deviation itself has the same units as the value being measured, and this is the square root of the variance. So the average itself is a random number. The variance expresses its spread, and the square root of the variance gives an indication of the accuracy that can be obtained, or the deviation from the true value in the same terms as the value itself. So the station, the closer the average will be to the true value. A very good and clear illustration of this is, for example, in satellite navigation, satellite navigation can give relatively high resolution, high accuracy, but the bandwidths of the receivers are not particularly high considering the accuracy that's obtained, and this accuracy is obtained because a very, very large number of pulses are used and they are averaged in order to give the accuracy that's obtained in that case, and this is true for any other communication. As we'll see later, there are some communication systems where even single pulses can give high accuracy, particularly ultra-wideband, which we'll take a look at, and the newer variants of the Wi-Fi, of the 802.11, and we'll take a look at these later on, and we'll see that these high accuracy versions all have very high bandwidths and high clock rates. Okay? Okay. I've been talking now about the way I define positioning. We talked about time of flight of signals. There's also parameter is the direction of arrival. When we want to find location, we want to find the coordinates of a target, then we use both the measure of the distance to the target and the angle of arrival. These are three different classifications or three different ways of taking this basic time of flight or propagation determined measurement and the wavefront direction measurement and changing them into actual position information. So here we have three classifications. The first called rho theta, where rho is the distance between a reference station and a target, and theta is the direction of the wavefront itself. Okay, so here we have three cases. Here we have one reference terminal, and we can determine the coordinates in 2 dimensions of the target as shown by these relatively simple expressions, as the x coordinate and the y coordinates are functions of the distance measurement and the time of arrival or time of departure, depending on whether the reference is a transmitter or a receiver, and the directions are reciprocal, so it's the same whether the target is transmitting or it is receiving. Okay, so this is the rho theta situation where we have one reference which can determine or send out signals both in a given direction. This is comparable to the radar situation where the direction is known by the position of the antenna, and the distance is measured, as we shown in that earlier slide, by measuring the in the case of radar, back and forth. In the case of one direction signal, it would mean that the target would determine the distance between the emitter and the receiver by measuring the propagation time. So here we have one reference terminal. Here we have a case of 2 reference terminal, which uses the time of arrival of the signals. Again, we'll assume that the target is transmitting, so each of these reference will measure the time of arrival of the direction of arrival or angle arrival in reference to a given direction, and plugging those directions of arrival or angles of arrival into these expressions here, the x and y coordinates of the target can be determined. So here we have 2 reference stations and a target in order to determine the location of the target given the angle of arrival of the signals. The third case is called rho-rho. We have omnidirectional reference stations, and the reference stations, in the case of that they are receiving, they will determine the rho. They'll determine the distance between the reference station and the target, and the location of the target will then be the intersection of circles in 2 dimensions to give the location, the x and y coordinates of the target. These are not linear equations. There is a possibility of the ambiguity by having these rho 1 and rho 2 measurements. The target could either be 2 locations, and so some additional information has to be known about the target's location in order to determine that this particular intersection here is where the target is, and this can be determined. In other words, these equations here have 2 solutions, and the right solution depends on some knowledge of approximately where the target is located. Okay, if in the case of 3 dimensions, these would be spheres instead of circles, but then there would be an additional equation. In order to eliminate this ambiguity, a 3rd station is necessary in 2 dimensions in order to have another section, which will give a unambiguous indication or estimation of where the target is located. The distances rho in all of these cases can either be through time of flight or through propagation methods or by receiving signal strength. Okay, now let's look in a little bit more detail of at the time of flight. Time of flight refers to all the measurement methods based on electromagnetic time. In the first case, the distance between the 2 terminals terminals 1 and terminal 2, can be found by directly measuring the time of flight when synchronized clocks are available at both ends. Terminal B notes the time of reception of the epoch of a transmission received from A and subtracts it from the time of transmission of the epoch which it receives from A. Epoch, as I mentioned earlier, is a definable, measurable instant on the transmitting signal. This does not work on CW signals since the particular instant is not detectable, but this works with pulses or with a protocol which allows determining an instant between different points on the signal or different fields in that protocol. The problem with this arrangement here is that the clocks have to be perfectly have to be synchronized perfectly. This may require very, very accurate clocks on both ends, and in many cases this is not a suitable solution since very, very accurate clocks are expensive, and drift is also a problem. So this will be difficult to use this when we're talking about measuring the distance between two terminals. When we have one reference station or numerous reference stations and a single target, it is possible to use time of arrival, which is the case in satellite navigation, GPS and GNSS, and we'll see how we get around, we'll see later how we get around the fact that the clocks are not synchronized. And finding the distance between two terminals, without having to have synchronous clocks on both ends, we would use a transponder, and this is case 2. This is two-way time of arrival measurements. Here we have one-way time of arrival. Here we have two-way time of arrival measurements. And in this case, both times which are used, the propagation time, are located on one end of the link. And here we see that, for example, side A signal, side B will receive the signal, and it will, when it's connected to its receiver, and after a very precise given time after reception, the signal will be transmitted back. The target has to have both a transmitter and receiver, as does the source. The signal will be transmitted back, and the second time will be measured at the source of this link. At the initiation of this link, this is the relationship between it. The 1/2 indicates that we're talking about round trip time, and this tau is the time between reception and retransmission at the target itself. This is also used in many communication systems, and we're going to see examples of this later on as well. So this method is needed when we have to measure a distance between two terminals, and this cannot be done in the case shown here because of the fact that the clocks cannot be synchronized, and here it's both measurements T1 and T2 are made on using the same clock, the same size side of the terminal. And of course the time delay between reception and transmission has to be known and has to be given to the terminal that does the actual computations, that calculates this delta T, and the distance then is delta T times the speed of light. I might mention that when there are continuous signals and there could be interference between the sending and the receiving signals, two different frequencies can be used. Instead of transmitting very narrow pulses on the same frequency. Obviously, this time tau has to be longer than the pulse time if pulses were sent here, unless there is a way of separating the signals here, the transmitting and the receiving signals. So it's possible also to use different frequencies in order to prevent interference between the transmitting and the receiving signals at the source. Okay, keeping in mind now the problem with the time of arrival, the basic problem of having synchronous clocks on both ends, this is solved by using the time of arrival method, which we need for in 2 dimensions for determining the location. Here we determine the location of the target and not just its distance. And here we have 2 reference stations whose locations are accurately known, their x and y coordinates are accurately. And the parameter, the important parameter here is the time difference of arrival. Let's assume that we have the target is transmitting and the reference stations, I hear some noise here on the...
Sorry about that. Thanks, Ellen.
Okay, here we have the target is transmitting, and since these reference stations are different distances, they will take a longer time for the signal from the target to be received at the reference terminal 1 than it is at reference terminal 2. So there'll be a difference of time, T1 minus T2. This gives us the important parameter here. This is converted to distance by multiplying this distance by these times by the speed of light. So we get the differences. We don't get the distances themselves, we get the difference in distances, and then we can determine the coordinates, or we can determine the coordinates here of a hyperbola. A hyperbola, which has 2 branches, as you can see here. This is the equation of a hyperbola. And this, when we have 2 terminals and 1 target, we are able to determine the locus of the target. We can determine that the target is someplace on this hyperbola. This is analogous to the case that we saw earlier where we measure distance and we note that the target is someplace on a circle. On a circle, in this case, we know that the target is on a hyperbola. We don't know yet where it is on the hyperbola. We would have to have another set of measurements in order to determine where exactly the target is. So this, again, this formula here, you can see it from the geometry of the situation shown here, and you can determine this formula here. For convenience, both reference stations are on the x-axis. The origin is in the exactly between the 2 reference stations. The actual coordinates of the reference stations can be different simply by rotation or translation of the values used in this expression here. Okay, now note here that we have a one-way measurement. One way, again, the target can either be the transmitter or the receiver, but it is a one-way measurement, and it is not necessary for clocks to be synchronized between the target and the references. It is necessary in order to get these times of arrival and have meaning to them. It is necessary that the clocks in the 2 reference stations here are synchronized. Now, in this slide, we have 3 base stations. And now we take 2 sets of time difference of arrival measurement. We have the first one, 1 and 2, as we had earlier, and now we have an additional reference station, which F3 together with F2 with the same type of geometry as we saw earlier would give us another parabola shown by this solid line here, in addition to the parabola on the dotted line. And now the actual coordinates of the target can be determined as the intersection between the 2 hyperbolas. Okay, so now we have 3 references, and we have 2 equations with 2 unknowns. This also can be ambiguous. It doesn't seem to be ambiguous here, but I think you could easily see that with different distances here, we could have ambiguity, just as we had in the earlier case when we had the intersection of circles. So an additional station would be needed in order to eliminate any ambiguity here. So we would have to have, in 3 dimensions, we would have to have at least 4 reference stations from which 3 independent time difference measurements are made, 4 fixed stations for 2D and 5 fixed stations for 3D are required in order to remove ambiguities. This is also this arrangement here. Time difference of arrival is used very commonly, for example, in terrestrial cellular networks, as we're going to see later on. Here we have 2 different cases of time difference of arrival. We have a unilateral case and a multilateral case. Here, in this particular case, if the reference stations are transmitting, in this unilateral case, the reference stations are transmitting, and it could happen when they're all using the same frequency that there'll be interference between the epochs of the 3 different transmitting stations. The receiver won't be able to determine them because they'll send on the same frequencies. If we talk about pulses, for convenience, we'll talk about pulses. We'd have to separate the pulses in order to be sure that there won't be any overlap between the transmitting pulses of the 3 different reference stations here when they're received by the receiver. Here we have tau 2 and tau 3 separate the times of transmission of the pulses in the unilateral case, and they have to be taken into account in order to determine the time differences of arrival. Here we have 2 time differences of arrival where the time differences of transmission are subtracted out in order to give true time differences of arrival. In the multilateral case, when the target is transmitting, this problem doesn't exist, and a pulse or an epoch sent from one transmitter can be received without interference at the 3 reference stations. So here we have, as shown here, the 2 different time differences of arrival, which are used as shown on the previous slide to determine the intersection of hyperbolas and the estimate of the target location. Okay, to summarize, time difference of arrival is based on the propagation time of flight. It's used when no 2-way communication is possible or desirable. Here we have 1-way communication at both the targets and the reference stations. there has to be at least one more fixed terminal than the number of coordinates. The fixed terminals themselves have to have their clocks synchronized, and their positions have to be known exactly in order to determine the unknown position of the target. This is used in terrestrial networks for GPS or GNSS backup or independent accurate positioning, and we're going to see examples of this later on. There's another use of propagation time, which is not a question of measuring times of pulses, but rather measuring the phase. And I mentioned earlier that an epoch on a signal has to be known in order to make a measurement of a time of arrival or time of flight. In the case of the multi-carrier phase difference method, CW, continuous wave signals, can be used, and what is determined here, or the measuring parameter here, is the phase difference. Here we have two signals, and here we can see that the receive is delayed in phase by theta, as we see here. So by measuring the phase, if we have a reference phase, of course, at the receiver, we know the phase of the transmitting signal, and we can determine the phase of the receiving signal by measuring this phase difference. The time, propagation time, can be determined from the wavelength. Here we have the relationship between the time and the wavelength, either frequency or wavelength. We have here how theta is related to time. Okay, and in terms of wavelength, we can see it here, but note that this same phase will be noted even further on if the time is greater than the time that takes the signal to propagate over the distance of a single wavelength. There will be an ambiguity of the distance. The ambiguity would be by a number of wavelengths, n, which is not known, a number of whole wavelengths. So here we can have the phase at this point, and we would have the same phase would be determined at this other point here, and so on and so forth. That would mean that the distance can be determined by the phase plus the number of wavelengths here. So here we have this problem of ambiguity, which depends on the wavelength of the signal. In the case of very, very large wavelength signals, very low frequency signals, and there are and were a location systems which operated at very, very low frequencies, even as low as 10 kilohertz, which had very, very long wavelengths, which meant that this ambiguity of the number of wavelengths was such that it was possible, if some approximation of the location was known, the distance could be determined relatively accurately by measuring the phase difference here. But when high frequencies are used and the wavelength is short, then this ambiguity is a problem. In order to get around this n can be canceled out by using two different frequencies. So if we have the same equation here at two different frequencies, f1 and f2, we can eliminate the n, and we can determine the distance by simply measuring the phases of the signals of the two different frequencies, and this will give us the distance without having to worry about the ambiguity here. And this again means sending multiple signals at multiple frequencies. In this particular case, the distance can be determined without ambiguity as long as it is less than this quantity shown here. This gives a upper limit of the distance that can be determined without ambiguity. If we make a plot of frequency versus the phase of the signals that are being received, we will get plots as shown here. Here there is some noise in the signals. We have two different distances here. Let's take the case of measuring 20 meters. We have this is this blue line here, and it's not straight because of noise, but we can see that the difference between the 20 meters and the 30 meter distances between the initiator and the target, the phase measurements have different slopes. Notice here that this has a smaller slope. This has a larger, the red signal has a larger slope, and this phase slope is what determines, through this relationship here, determines the distance. And also you can see here that there is a limitation of measuring phase between, in this particular case, between plus or minus 180 degrees. Okay, so this is a method which, I'll give you an example later on. We're going to see an example how this may be used, but this is also a valid way of, instead of using time of arrival, using phase arrival. And again, this requires signals, narrowband signals, and filtering. The time depends on the number of frequency used, of course, and also the amount of noise that has to be filtered from these signals will also be, just as in the case of the time of arrival, by having a larger time and using narrower filters, the accuracy can be improved. Okay, so in this case, whereas here we need narrowband signals as compared to the case where we want wideband signals in the case of time of arrival. For phase of arrival, we use narrowband signals. And again, this was reflected in the timing, or the time duration, in order to perform the measurements. Okay, let's take a look before we go on to the next parameter here of the sources of error. Obviously, since we mentioned that the reference stations, their position has to be known, how well it is known is a source of error. The accuracy of the reference stations determines the accuracy that the target location can be known. There will also be errors in measuring the timing. Clock errors will contribute. Clock jitter will contribute to errors here. System noise, obviously, interference. Multipath, we saw this on that earlier diagram where we saw several signals being received over different paths, and there is a problem of determining signal is the line of sight signal, and this is also a source of error. And a very important parameter which is needed to determine the accuracy of the time of flight methods, and that's the dilution of precision, DOP. Here which depends on the relationship between the target and the reference stations. Here we have two reference stations in the row method, where we have the error, possible error by noise, for example, in the signals in measuring the row values or the distance between each of the base stations and the target, and there will be a gray area here where the target could be anywhere within this gray area. When the reference stations are located either very close together or very, very far apart, this gray area will be larger and there will be a higher error, or larger accuracy in the signal, even though this is for a given amount of noise, and the other parameters being the same in the two cases, the actual errors will depend on the location of the reference stations. So it depends on the layout of the fixed stations in relation to the target, and again, if the stations are close together or very far apart, this will enlarge the uncertainty region of the target's position. Here we have multipath. The multipath. This is probably the most serious cause of distance measurement and location errors, particularly in indoor applications. Obviously, if the time of arrival or the time difference of arrival are measured on non-line of sight paths, the distances involved will be greater than the true line of sight distances. Usually there are many paths over which the transmitted signal is propagated. If the receiver can measure the time of propagation for each path, it will be able to recognize the shortest path, which is the true distance between the transmitter and receiver, unless the line of sight is totally obscured. High bandwidth signals potentially give better discrimination of multipath returns, and in order to distinguish between the arrival times over two different paths, the minimum receiver bandwidth must be approximately as shown here, where we see that the minimum between two different paths plugged into this formula here will give the minimum wavelength in order to distinguish between the different paths. And we will see later on, when we have very high bandwidth signals, for example, for ultra wideband, and also for the newer Wi-Fi systems, the multiple path times of arrival or times of flight can be measured, and the shortest path is considered to be the direct path, and this is used in order to find the propagation time and the distance between the transmitting and receiving terminals. Here is another look at the dilution of precision, and this gives an expression which indicates how this number here, this dilution of precision, can be determined mathematically to be a number which will show the type of accuracy can be determined. I'm not going to give the details except to show here that if we have the standard deviation of the measuring of the distance, in other words, we're going to measure, let's say, assuming that this cell phone is measuring the signals, the time of flight of the signals from three different reference terminals. It'll measure this time of flight with a particular accuracy here, and a standard deviation here, and we can relate this to the standard deviation of the parameters of the target using this expression here, and this involves determining the DOP, the dilution of precision. Okay, and this can be done before the location. If the location is approximately known of this, then it's possible to determine the geometry. It's possible to determine. I don't. I don't have that slide in this particular course here of how this is determined, but this is determined from geometry only. The number here of the dilution of precision, and given a precision of measuring the distances, this dilution of precision is what determines actual ultimate accuracy of location of the target. I see there was a question. I see there was a question here. Before we go on to this R receives a signal strength, I'll take a look at here, which was in the chat. Again, it's probably more convenient if these questions are in the Q&A. I see there are questions in the Q&A. We'll deal with them when we take a break shortly. Let me just get to this question now. Before we go on here, we're talking about slide 8. I'll go to slide 8 and see what this question is. Okay. The question is the true value a calculated or expected value? Again, when we're talking about a single pulse, as I generally was talking about here, we're talking about the actual value, but it can be just as way. It can be an expected value as well. It doesn't really matter whether it be a single value itself, or it can be the timing would be done multiple times, as I mentioned here, by making a large number of values. If the clock is off, these clocks are not synchronized, then we will not arrive at the true value. If these clocks are not synchronized, we will not get from an expected value, we will not get the true delta time here. If the clocks are synchronized, then the expected value will be the averaging process we showed earlier, and this would give more accuracy to the result. The same is the case here. If multiple measurements are made, the multiple measurements will clean out the noise on the signals, but in this case here, they will not clean out the clock drifts and the clock rates of the two terminals. So when we're talking about a particular value, yes, we can talk about or an average value with the advantages that I mentioned earlier on. Okay, I hope this answers the question. Also, there's another question about the slide 16. Something wasn't clear here. The values here, this is the SR. R is the row here, indicates the row. This is the standard of the measurement. Again, what we're measuring here, we're not measuring location directly, as we saw earlier. We're not measuring it directly. The actual measurement is the distances here to each of these terminals in this particular case here, although this is true just as well, this dilution of precision, also in the case for time difference of arrival. But here we're talking about the time of arrival situation where we have direct measurements between, for ease of explanation here, between transmitters and the cell phone receiver. So we're talking about the accuracy that we can measure the distance, which is the same in the three different cases here. So this relates the accuracy or the standard deviation of the measurement itself to the standard deviation in the coordinates which we need to know what the location of the object is. I hope this answers it. I think that maybe as we go along, some of these problems may work themselves out later on, but if not, you're welcome to ask when we talk about later slides. We're going to get into examples of these things later on, and I hope that things will be clearer then at that time. So thanks for your questions. Let's move on now to where we were. We're going to talk about received signal strength, which is another type of observation, measurement or observation, which is used both for positioning and for location. Received signal strength Okay, received signal strength is based on the inverse proportionality of signal strength to the distance between the terminals, which means very simply the further you are away, the lower the signal will be, the weaker the signal will be. The transmitted radiator power has to be known in order to directly calculate distance from signal strength. So obviously the strength of the signal is going to be weaker as the target gets further away from the transmitter. Will also be weaker if the transmitter or the initiator transmitting signals is weaker. Okay, so radiated power has to be known. There are different classes of location system. There is proximity, where the approximate or location estimate depends on whether the signal can be received or not. If the object is too far away from the transmitter, there won't be any reception at all. As long as the signal is being received, it's known that this signal, that the target is near the coordinates of the transmitting beacon. A more accurate, potentially more accurate estimation of distance is by measuring the path loss, which this depends on the electromagnetic wave propagation and empirical observations of determining the path loss. If the path loss is known, and again, transmitter power is known, also an estimation can be made of the distance between the terminals. The third class is database comparison, where measurements are made in advance of signal strength from various terminals to a target. When the target is in known positions within a particular area, and then when a true measurement has to be made from a true target, then a comparison is made with a database in order to get an approximation of where the target is. Note here particularly the potentially best way to get an accurate distance measurement is through using the path loss, but the path loss is going to determined greatly by the environment. If there are reflected signals, either certainly from the ground or from buildings or whatever, this is going to affect, or the multipath signals are going to affect the received signal strength. So this is a source of inaccuracy in using the path loss method. Okay, let's take a look here at how this works. Received signal strength is an indication of the distance from the transmitter when the transmitter power is known. So here we have received signal. We measure a voltage on the output. Receivers, many receivers, receiver chips have an RSSI, receive signal strength indicator output. The voltage at this output can be measured, and this voltage can determine the RF input level at the input to the receiver. At the input to the receiver, the RF input level can be determined by the signal strength measured by the at the output of this RSSI terminal on the receiver, and this will can be related to the signal strength can be related to distance when the antenna gains are known and when the transmitting power is known, and then we get these. Here we have three different references. In an earlier slide, here we have three, and three equations can be determined when the distances are known by from three different terminals. There'll be three different RSSI measurements, as we can see here, and here we have three equations with two unknowns, and an estimation can be determined of the target. Okay, in the case of free space propagation, distances can be determined relatively accurately. In free space, we can determine accurately the received power, the received signal power, by knowing the transmitter power, the gains of the transmitting and receiving antenna, length of the signal, and the power depends then on the inverse square of the distance between them. Okay, so all these parameters are needed in order to determine the received power. This will give the received power, which can be determined as shown on the previous slide. So here we are determining received power by a ratio. We can also determine this by decibels. Usually the phase or the path loss is given as a decimal number in dBs, and we have this taking this logarithms of both sides here. We can determine the decibels as shown here, and here we have a logarithmic relationship of loss and decibels to the distance. Again, here note that the path loss, the larger the distance, the larger the path loss. Okay. Okay, this is, again, we can talk about path gain. The path gain would be the negative of this, or the would be inverted. This term would be inverted. Okay, so we see here that the received power then is proportional to the received signal strength, and here we have an expression of the received signal strength in dBm, received signal strength in dBm. Again, that's decibels referred to 1 milliwatt, and we have to know, if we know this, the dBm, we know the antenna gains transmitting power, and we have determined the received power by measuring it, the received signal strength indicator, as shown here. We can determine the path loss, and by using the path loss in this expression here, we can find the distance. Okay. These expressions, this inverse square law, is relevant only when the distance is greater than a relationship which depends on the size of the antenna and the wavelength itself. Normally with the high frequencies that we're determining, we're talking only about any distances within only a few meters from the transmitter. This is true. This can be a general estimation, but this is true in the case of free space propagation where there are no reflections. Okay, what happens if there are reflections? If there is a reflection, and here we have the simplest case where we have only a reflection from the ground, only reflection from the gain, and here we're going to talk about path gain since it's more intuitive to look at the signals as being weaker with distance. In the case of path loss, the path loss goes up with distance. Here we're talking about path gain. The relationship between path gain and path loss is shown here. And in this case, the reflections will cause a different type of a response than we saw in the earlier in the previous slide. This red line here shows the type of response when we have only a reflection from the ground. We see that there are distances where the signals from the reflected signal from the ground and the direct signal aid each other in phase, and where they are opposite to each other in phase. So this gives us this fading effect that we can see here. Beyond a particular distance, we see that there is a difference from this inverse square law that we saw in the line of sight case, and here we have a relationship which depends on an exponent, which we call this exponent n, where n is 2 in the inverse square law case that we see here. And it can be some other value when there are additional reflections. Here, this is the case that we have only reflection from the ground. If there are additional reflections, the shape of this, or the ultimate path gain reduction, the slope of this reduction, will depend on this value of n that we see here. Okay? So here we have the case again of the line of sight, and here we have the case when there is numerous reflections, and in the case that we have here of a reflection only from the ground, n would be equal to 2. Okay, this formula here, excuse me, I didn't mention that this is the case where n is equal to. This is the case where there are multiple reflections and the exponent will be either greater than 2 or maybe less than 2. And we will have this expression here, which could be used to determine the path gain, and used in order to determine the distance using this received signal strength method. The problem here is that in many situations you won't be able to determine exactly even in a particular location. There may be 3 reflectors or many more reflectors. 2 points will differ because of the variance in the types of reflections. And even if we can determine a particular average n by making a large number of measurements throughout an area, there will still be a random variation in the path gain, and this is expressed by this x sigma term. X is a random variable with having a standard deviation of sigma. Okay, so this is an expression which can be used as an approximation of the path gain. When the path gain is known, we can make an approximation of distance. And also, I can just show here in this particular individual case of having only reflection from the ground, this point where there is a constant slope of the path gain. It depends on the wavelength and the heights of the antennas on both ends of the link. And here again you have information of the parameters of this particular graph that's shown here. Okay. Again, multiple measurements can be taken in order to determine what n would be. I have a diagram here, I believe. Let's see the next slide here. We can see many measurements are determined. We want to find out what this value of n is. Here we have the n. We want to find out what it is, and we can determine a regression curve. There's a formula. Once you have all of these small dots are measurements, and the approximate n can be determined, or an n value can be determined for a particular environment. And of course, the actual result will have a particular standard deviation, and this is indicated by this term here. Okay, and here you can see some examples to give rough values of use of this equation in different environments, and you can see them here where n measures values according to measurements. It also depends on the frequency, and I took this from some information. Much more information would be necessary for actual use, direct use, but this gives an idea of the types of variations in this particular, say, retail store environment. Would give relatively large standard deviation, and this shows that the RSS measurement in this particular case is not particularly accurate because of the high standard deviations that can be expected, but this could be used as a, say, rule of thumb estimation of distances from the received signal strength measurements. Okay, there would have to be some estimation of this D0 here, to see where there is the turnover between the crossover between the approximate line of sight. Let me just go back a distance. Here we see the variation of the signal strength is around approximately the line of sight. The line of sight is on this blue dashed line here, and where the definitive slope occurs is at a particular distance D0. In this particular case, for example, in an indoor environment, this would have to be estimated. In many cases, in an indoor environment, this D0 is taken to be 1 meter. Okay, so this would have to be estimated. In this particular case, you could take, say, roughly 1 meter, and then you could use this slope that was determined here is approximately 3 in order to make estimations of path loss equation. Earlier, note the path loss equation here. We have the path loss and the path gain are related by the minus sign, as I showed you earlier. Here we have path loss. Using path loss, the distances can be estimated. Okay, so in any case, we can see that in many environments, the use of RSSI or R received signal strength measurements, while being very convenient, it's also not very accurate because of the different reflections that can occur between any 2 points within a particular environment. And to get around this, many systems which are relatively accurate use what's called fingerprinting, also called pattern matching, where there are multiple access points, reference terminals, and where there are multiple survey points where received signal strength measurements are made at known positions within a given area, shown by X here. Given positions within this area, a database is created from this information. This is the test phase, or setting up this database phase. And once the database is set up in a true measurement, a device being at some point within this boundary would also make measurements to the different, here we have 3 different access points within this boundary, would make measurements, and those measurements in the actual measurement case would be compared to all of the measurements in the predefined database. And from this comparison, in this comparison, the closest reference point or closest database point would be considered to be the location of the actual target. Now these points here, normally they would be done on the grid. If you would divide this up to a grid, okay, of grid, I can make say lines here, areas here, having a grid, and there would be a certain resolution. This grid, these data point, these reference stations would be someplace on points within this grid, and these locations could be determined these are determined in advance. And then again, as I tried to indicate earlier, measurements are made by the target, then the comparison will give, for example, if here we place the target here, this is the target, we know that its signal strength can be closest to this point in this database point, and we can know that this is somewhere within this region here, and this gives us an estimate of the location of the target. Here you can see it better, I think, on the next slide. Here we have the database entries. Here the ends here are the particular square which I showed you in the way that the database, the way that the area is divided up into coordinates points. These coordinates points, these are not exponents. These sample positions here are denoted by a number. There are X and Y. Also, the element orientation may be indicated, since this will also determine the signal strength. So this will give the coordinates of a measurement in the database, and these will give the actual measurements that are made during that test phase of determining the database. So there will be a number of database and on the number of regions within that database where the test measurements were taken, the online or the real vector of the real desired target have values of and S3 are the signal strength from the three different access points, and they are compared using this relationship here. Using this relationship here, these measurements are compared to all of the points within the database, in order to find the closest neighbors, called the L nearest neighbors. The example I gave you on the previous slide showed there were three nearest neighbors, and then by averaging the coordinates of those nearest neighbors, we can get an approximation of an estimation of the target location. Okay, I hope this is clear, and we can move on to here. It is a flow diagram showing basically what I mentioned before, how this important RF fingerprinting method is used. And again, I like to emphasize this is done, although there is an inconvenience of preparing the database in advance, but this is necessary to get fairly good accuracy, considering the vagaries of using the propagation or the path loss method, which we saw has large deviations because of the multipath reflections. So here we have a flow diagram for this positioning method. We have fingerprinting method. We create the database in advance at a particular area. This involves, again, then in the case when the true measurement has to be made, measurements of signal strength are made to the target from each access point, or the other way around. The target could transmit and the access point will receive. It works in both directions. This location data would be sent to a location coordinator. There would be comparison to the database as shown in the previous slides, find the nearest neighbors, and then get the position estimate. To summarize RSSS, a relatively easy implementation on the existing network, since many systems or most receivers have a receive signal strength output, and this can be measured. Modulation type or data rate or epoch is not necessary to be known here. No synchronization or timing is required, so there's a low cost. However, on the other side, we find that the time of flight methods are quite more accurate. Accuracy is much on the environment. Database may be needed. In the case of the fingerprinting method, which we saw just now, transmitting power is needed for path loss estimate in the case where the path loss is used in order to determine distance. And of course, equipment orientation will affect the signal strength, and as well as nearby objects and obstacles. Okay, the next subject is time angle of arrival. We're going to take a short break here. We'll take a break until 15 minutes before the hour, 45 minutes after the hour. I'll take a look at and we'll move on, and I will have to increase the pace. I'm trying to give you the basics here. I think it'll make it easier to understand what we have going on, but the pace is going to increase after the break. But in the meantime, I'm going to look at your Q&As, take a welcome break for all of us for 10 minutes, and then we'll be back at 15 minutes before the hour.
And Alan, just remember to mute your line. Yep, thank you. Enjoy the break, everyone.